Vibration analysis. Procedures for accurate evaluation of machinery condition. Common machinery. Part 3. In this video, we will talk about procedures for accurate evaluation of machinery condition. Analysis in common machinery includes 1. Electric motors. 2. Steam turbines. 3. Pumps. 4. Compressors. And 4. Fans. Let's start with vibration analysis about procedures for accurate evaluation of common machinery. Analysis of electric motors includes: Number 1. Motors out of magnetic center. 2. Broken rotor bars. 3. Turn-to-turn shorts in winding. 3. Vibration problems in synchronous motors. 4. Siren effect. And 5. Solo data on motors. Electric motors can have a limited number of problems, just as any other equipment group. However, some problems occur only in electric motors. Electromechanical problems in electric motors must be further divided into induction and synchronous motors. The following electromechanical problems occur primarily in induction motors. 1. Motor out of magnetic center. 2. Broken bars in the rotor. 3. Turn-to-turn shorts in the stator windings. 4. Vibration at line frequency, 50 or 60 cycles. 5. Siren effect. 6. Overloading. Induction motors are designed to operate at a fixed speed. For example, 900, 1200, 1800, and 3600 RPM are the most common speeds. However, these motors seldom operate at the synchronous speed. Generally, they operate below the synchronous speed. The difference between the synchronous speed and operating speed is called the slip frequency. The exact operating speed is affected by motor efficiency and load. A high-efficiency motor operating with little or no load may run at near synchronous speed. The stator windings are called poles. The number of poles determines the speed of the motor. To calculate the number of poles in a motor, divide 7,200 by the synchronous speed of the motor. For example, a 3600 RPM motor 7,200 divided by 3600 equal to 2 poles. An 1800 RPM motor has 7,200 divided by 1800 equal to 4 poles. A 1200 RPM motor has 7,200 divided by 1200 equal to 6 poles. A 900 RPM motor has 7,200 divided by 900 equal to 8 poles. Frequency is equal to events times speed. When some of the above problems occur, the motor speed and harmonics are modulated by slip frequency times the number of poles. These frequencies normally do not appear as discrete frequencies. Rather, they appear as sidebands or difference frequencies around motor speed and harmonics. The data from motors out of magnetic center, broken or open rotor bars, or turn-to-turn shorts in the windings are similar, and detailed analysis is required for accurate diagnosis. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common machinery. Analysis of electric motors. Motors out of magnetic center. This condition normally occurs when the rotor is not positioned in the magnetic center of the stator in the axial or lateral direction. An out-of-magnetic center condition could occur in the radial direction when there is an uneven air gap between the rotor and stator. This problem may not generate excessive vibration levels and is often overlooked because the data is not processed with enough resolution to identify the problem. For example, the data in Figure 20 was taken from a 3,600 RPM motor. This data could be erroneously diagnosed as looseness, misalignment, or even bent shaft because more resolution is required for accurate diagnosis. Figure 21 contains a 20 Hz window around 60 Hz. This data indicates that the motor is out of magnetic center. This data contains spectral lines with a line frequency of 60 Hz and a motor speed of 59.5 Hz. Motor speed has sidebands at a slip frequency of 0.5 Hz times the number of poles or 2. Or 0.5 Hz multiply 2 equal to 1 Hz. The sidebands are 58.5, 60.5, and 61.5 Hz. Please note, line frequency does not have sidebands. Figure 22 contains a 20 Hz window around 120 Hz. This data has enough resolution to verify the second harmonic of motor speed of 119 Hz, which is not a problem. The predominant frequency is 120 Hz, which is 2 times line frequency. The beat is available in 1800 and 3600 RPM motors with an out-of-magnetic center condition. Slower motors, 1200 RPM and lower, may not be affected as much by out-of-magnetic center problems because higher harmonics of motor speed are near 60 Hz. The 60 Hz frequency may appear as a discrete frequency when these motors have an out-of-magnetic center condition. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common machinery. Analysis of electric motors. Broken rotor bars. This problem is similar to the out-of-magnetic center problem. However, there are distinctive differences. The similarity is that rotor speed is modulated by slip frequency times the number of poles. A broken rotor bar, sometimes called open iron, creates a dead spot in the rotor. The resulting electrical imbalance can generate significant vibration levels at 1 and 2 times RPM. Since this problem is not interactive with line frequency, a spectral line at 60 Hz may not be present. Once again, the data must be processed with enough resolution for accurate diagnosis. Figure 23 contains data taken from a motor that has one or more broken rotor bars. On the 1000 Hz range, the diagnosis could be looseness and bent shaft. Figure 24 contains a 40 Hz window around 60 Hz. Motor speed is 59.5 Hz, and plus and minus sidebands of 0.9 Hz are present. Slip frequency is 0.45 Hz multiply 2 poles equal to 0.9 Hz, within measurement accuracy. The sideband at 58.6 Hz is higher in amplitude than motor speed, 59.5 Hz. This occurs when the amplitude of the modulator is greater than the carrier. In such cases, phase reversal occurs and can be observed in the time signal. This could indicate more than one broken rotor bar. Figure 25 is a 20 Hz window around 120 Hz. 2 times motor speed is 119.1 Hz, and sidebands 0.9 Hz apart are present. Also note that the sideband at 118.2 Hz has an amplitude greater than the second harmonic of motor speed. The above explanation also applies. An example of broken rotor bars from a motor at a different speed may provide some clarity. Figure 26 contains data from a 1200 RPM motor that has broken rotor bars. The vibration amplitude is quite high and the sidebands are visible on the 100 Hz range. Figure 27 contains a 20 Hz window around 20 Hz. The sidebands are 1.25 Hz apart. The delta F is equal to slip frequency times the number of poles, or 0.21 Hz multiplied by 6 equal to 1.26 Hz. Figure 28 contains a 20 Hz window around the second harmonic of motor speed. The sidebands are slip frequency times number of poles. In this case, the amplitude of the spectral lines at motor speed and the second harmonic are higher than the sidebands. Figure 29 contains the time domain signal. The time period between points 1 and 2 is motor speed. The time period between points 3 and 4 is 2 times motor speed, and the time period between points 5 and 6 is slip frequency times number of poles. Vibration analysis. Procedures for accurate evaluation. Common machinery. Analysis of electric motors. Turn-to-turn shorts in windings. Motor stator windings are often called poles. When some wires in the winding/pole are shorted together, the motor often slows down. When the motor speed is reduced, slip frequency increases. Figure 31 contains the data from an 1800 RPM motor that has turn-to-turn shorts in the windings. Motor speed is 29 Hz multiplied by 60 equal to 1740 RPM, and the sidebands are 4 Hz apart where delta F equal to 4 Hz. These sidebands are still equal to slip frequency multiplied by number of poles, i.e. 1 Hz multiplied by 4 equal to 4 Hz. Figure 32 contains the time signal. Motor speed, slip frequency, and number of poles are labeled. The above descriptions of induction motor problems can be summarized into 4 as follows. Number 1, motors out of magnetic center with broken rotor bars or turn-to-turn shorts all contain sidebands of slip frequency times number of poles around motor speed and harmonics. Number 2, motors out of magnetic center normally contain a spectral line at 60 Hz. Number 3, motors that have broken rotor bars normally have high amplitudes at motor speed and or the second harmonic. And number 4, motors that have turn-to-turn shorts in the windings have slower speeds and higher slip frequencies. Vibration analysis. Procedures for accurate evaluation. Common machinery. Analysis of electric motors. Vibration problems in synchronous motors. Half-wave rectification of a 60 Hz sine wave yields a ripple frequency of 60 Hz. Full-wave rectification yields a ripple frequency of 120 Hz. Half-wave rectification of one phase and full-wave rectification of another phase yields a ripple frequency of 180 Hz. Full-wave rectification of three phases yields a ripple frequency of 360 Hz. Some synchronous motors have power supplies that use diodes to rectify AC voltage and obtain the desired power for a desired speed. These motors can vibrate at significant levels when a problem occurs in the power supply or the controlling circuit board. The frequency of these electrical vibrations in synchronous motors can occur at 60 Hz in harmonics, 120 Hz in harmonics, 180 Hz in harmonics, and or 360 Hz in harmonics. Figure 33 contains data from a synchronous motor with an electrical problem. This problem was solved by replacing a circuit board in the power supply. Vibration analysis. Procedures for accurate evaluation. Common machinery. Analysis of electric motors. Siren effect. The siren effect in motors occurs as in any other siren. When a number of slots or grooves pass over other slots or grooves at the correct speed and air gap, a noise or sound pressure level is generated. Since this is a generated frequency, it is equal to events times speed. If a rotor has 38 bars/slots and the speed is 1776 RPM or 29.6 Hz, the frequency generated would be 38 multiplied by 29.6 Hz equal to 1124.8 Hz. As these slots pass over one point, the frequency is generated. If the slots pass over several points, as in a motor, the same frequency is generated. However, the sound volume is higher, and the frequency is modulated by motor speed. The vibration level on the motor may not be very high, 0.2 or 0.3 inch per second, but the sound pressure level can be quite excessive. Siren effect sound pressure levels above 120 decibel have been observed or pain is felt in the human ear at 120 decibel. An 1800 RPM motor with 38 rotor bars could generate a frequency of 1124.8 Hz, as in figure 34. Please note that plus and minus sidebands are present. The difference frequency between the sidebands is 29.6 Hz, or motor speed. Vibration analysis. Procedures for accurate evaluation. Common machinery. Analysis of electric motors. Solo data on motors. After the coupling has been installed and a motor has been set in place, the motor must be started and ran. After the motor finds its magnetic center, if it does, the shaft must be scribed. The scribe marker is essential for setting the proper distance between the coupling halves. While the motor is running solo, data should be taken. This data provides the last chance to identify imbalance, bent shaft, misalignment between the bearings center lines, bearings loose in the housing, defects in the bearings, and inadequate lubrication. Every plant in the world could save hundreds of thousands of dollars per year if solo data were taken on all motors, and if repairs were made before the installation is completed. The vibration should be recorded while the power is removed. Recording should continue until the motor speed is below 500 RPM. The coast-down curves for velocity, displacement, and acceleration should be similar to Figure 35, Figure 36, please see next slide to go, and Figure 37, please see next two slides to go, respectively, for pure imbalance. The curves were produced with the vibration calculator program and can be used to determine how much the vibration will increase for a given increase in speed. Additional data should also be taken at startup after the installation is complete. This data identifies all problems with the drive unit that are installation related. Solo, coast down, and startup data are essential for future reference, integrity of the new equipment, installation, and identification of potential premature failures. Vibration analysis. Procedures for accurate evaluation. Common machinery. Steam turbines. Steam turbines require special attention because of the high speeds involved, extreme heat, and the small lightweight rotors. These factors contribute to rotor sag or bow. Therefore, most all turbines should be slow-rolled for some period of time before alignment and operation. This slow rolling should remove the sag or bow from the rotor. Solo data and coast-down data must also be taken on turbines to determine the vibration response at various speeds and to identify imbalance, misalignment between the bearings, and natural frequency. Diagnostics can be severely complicated when the problem could have been identified from taking solo data first. Start-up and/or coast-down data must also be taken for records, problem identification, resonant frequencies, bandwidth, and amplification factors. If a turbine is not equipped with permanently mounted proximity probes, then data must be taken with portable proximity probes. Relative motion should be measured between the turbine bearing housing, the shaft, and the coupling. Some manufacturers of proximity probes have overemphasized the seriousness of mechanical runout, electrical runout, and glitches to the point that many analysts will not use a proximity probe except in tightly controlled permanent installations. Portable probes have been used for years with a high degree of success. The portable proximity probe is quite versatile and is essential for relative motion measurements. A limited number of problems can occur in turbines. For example, looseness, imbalance, misalignment, soft foot, resonance, and rubs. The net result is that most diagnoses rely solely on proximity probe data. Data should also be taken with a permanently mounted accelerometer. This is true because the frequency response curve for displacement is a downward and outward sloping curve. This means high frequencies generate very low displacement levels. The frequency response curve for acceleration is an upward and outward sloping curve. This means high frequencies generate large acceleration levels. See Figure 27 on the right or in Chapter 1 in the earliest video of this channel on Section Vibration Analysis Introduction. A Rubinette turbine can generate high frequencies somewhere around the number of buckets times speed. The data in Figure 38 was taken in the axial direction on a turbine housing. The 1224 Hz frequency is generated by the buckets hitting or rubbing 25.5 times each revolution. The 48 Hz difference frequency of the sidebands indicates that the frequency is modulated by turbine speed. The 880 Hz frequency indicates that the rotating unit is not hitting or rubbing the same number of times each revolution. Please note that 0.1 inch per second at 1224 Hz equals 0.03 mils of displacement and 1.99 Gs of acceleration. This problem would not have been identified with displacement. This points out the need to take data with an accelerometer on high-speed machines. Vibration analysis. Procedures for accurate evaluation. Common problems in the pumps. 1. Impeller contact. 2. Starvation. 3. Cavitation. In addition to the more general problems, a pump can have vane pass frequency and cavitation problems. Pump starvation, impeller loose on the shaft, and the impeller hitting something can all generate vane pass frequency. Vibration analysis. Procedures for accurate evaluation. Common problems in the pumps. Impeller contact. When the vanes on an impeller are hitting something, vane pass frequency is equal to the number of vanes times speed. A pump rotating at 1776 rpm that has 4 vanes on the impeller would have a vane pass frequency of 1776 divided by 60 multiplied by 4 equal to 29.6 multiplied by 4 equal to 118.4 Hz. When an impeller is hitting something, two types of problems normally exist: residual imbalance and vane pass frequency. In this case, there are two frequencies in two problems. Figure 39 contains a frequency spectrum and time signal. The frequency spectrum has a spectral line at unit speed and at vane pass frequency. The time signal contains a high frequency riding a low frequency. The low frequency is unit speed, and the high frequency is vane pass frequency. Vane pass frequency is in phase with the fundamental. If the impeller was loose on the shaft, the vane pass frequency would be modulated by unit speed. The data in Figure 40 was taken from a pump that has 5 vanes. Vane pass frequency is changing its phase relationship to the fundamental because the impeller is loose on the shaft. The sidebands of unit speed on the low side of vane pass frequency are higher in amplitude because the frequencies are out of phase most of the time. The lower level sidebands of unit speed on the high side of vane pass frequency are present because the frequencies are in phase some of the time. If one or two sidebands were only on the high side of vane pass frequency, this would indicate that the signals are in phase. The impeller is hitting something each revolution. Vibration analysis. Procedures for accurate evaluation. Common problems in the pumps. Starvation. Pump starvation occurs when enough liquid is not present to fill each vane on the impeller every revolution. When this occurs, the amplitude of unit speed can be quite high, as in Figure 41. Pump starvation is often confused with imbalance. However, starvation has the following characteristics. Number 1, since each vane on the impeller is filled to varying degrees each revolution, the amplitude can vary each revolution. Number 2, the time signal could have some distortion. And number 3, if the pump is driven by an electric motor, the amp load on the motor may be less than normal. Starvation can also occur when foam is mixed with some slurries. Low amplitudes of vane pass frequency can also be present with starvation. Vibration analysis. Procedures for accurate evaluation. Common problems in the pumps. Cavitation. When a pump is not operating at the correct point for the pump curve, cavitation can occur. This phenomenon normally occurs when the suction intake is restricted, and the liquid tends to vaporize while coming off the impeller. This process generates noise and, to the human ear, may sound like the pump has failed. The frequency spectrum from a pump that is cavitating normally contains a spectral line at vane pass frequency on top of noise, as in Figure 42. When cavitation occurs, operations or personnel should be contacted to correct the problem. Vane pass frequency and harmonics at relatively high amplitudes are often measured on vacuum pumps. This can be caused by bent shaft and buildup in the pump, or improper clearance. However, this problem is most often caused by improper operation. These pumps need a water seal for proper operation, however, too much water can generate high amplitudes of vane pass frequency, as in Figure 43. Diagnostics of pump problems can be improved and expedited by installing a pressure transducer in the discharge line of the pump. Pressure transducers measure pressure fluctuations. They are calibrated in MV/PSI and the output can be processed on a real-time analyzer. The frequencies measured are 40 frequencies of the fluctuations, and the amplitude is the amount of fluctuations measured in PSI 0 to peak. Vibration analysis. Procedures for accurate evaluation. Common machinery. Compressors. Compressors compress some form of gas, come in various configurations, and operate in much the same way as pumps. For example, some compressors have a given number of lobes or vanes on a rotor. They generate vane pass frequency as do pumps. However, compressors may not cavitate. On screw compressors, vane pass frequency is calculated by multiplying the number of flights on the screw times the speed of the screw. Some compressors have two rotors, and each rotor has two or more lobes or vanes. The rotors can turn at the same speed and have timing gears. These compressors can generate frequencies at rotor speed, 2 times rotor speed because there are 2 lobes or vanes on each rotor, and 4 times rotor speed because there are 4 lobes or vanes on the 2 rotors. Harmonics of each frequency can also be generated, as in Figure 44. With this design and the close tolerances involved, overall vibration levels often exceed 0.3 inch per second. Pressure transducers should be installed in the discharge line of compressors because the measurement of pressure fluctuation is often required for accurate diagnosis. Figure 45 contains the time signal and frequency spectrum from a pressure transducer installed in the discharge line of a screw compressor with 4 flights. Vane pass frequency is 530 Hz. The static pressure is 92 psi, and the measured pressure fluctuations are 17%. Fluctuations are 16 divided 92 equal to 17%. This is excessive by most standards. In some applications, pressure fluctuations are held to 2 or 3%. Vibration analysis. Procedures for accurate evaluation. Common machinery. Fans. Fans can generate blade pass frequency, which is the number of blades times speed. This frequency normally occurs when the blades are hitting something, the housing is quite flexible, or an acoustical resonance is present which equals blade pass frequency. The more typical problems, such as imbalance, looseness, misalignment, bent shaft, and defective bearings, are discussed in other sections. Thank you.